It's a pleasure to introduce Rosario Fazio. Rosario received his PhD in physics from the University of Catania in 1990 and is currently a senior research scientist in the condensed matter and statistical physics section at the Abdus Salam International Center for Theoretical Physics in Trieste. He is also a professor of theoretical condensed matter physics at the University of Naples in Italy. His research spans theoretical condensed matter physics and quantum information science, with major contributions to quantum transport in nanodevices, mesoscopic superconductivity, quantum simulators, and many-body quantum systems. In his lecture today, he will focus on one of the, let's say, most central questions of modern physics. So why the macroscopic world appears to be classical, while in its fundamental bricks obey quantum laws. So building on groundbreaking experiments recognized by the Nobel Prize in Physics that demonstrated quantum behavior in increasingly large systems, the talk will highlight how superconductivity circuits and qubits have become a leading platform for investigating the quantum classical transition and for developing quantum technologies. Please.
Thank you very much for the kind introduction, and thank you very much for the invitation. So, as Giovanni said, I will start talking about the last Nobel Prize 2025, which started showing that certain macroscopic objects maybe behave like giant atoms, and then I will move and connect to the more recent developments where these objects, these superconducting nanostructures, are used for quantum technological application. So I apologize with the experts. I will keep the presentation at just a very general level. So let me start with 2025, which was a very special year for quantum mechanics. It was declared by the United Nations as the International Year of Quantum Science and Technology. This is the document where all this started. So essentially the idea was to nominate a year devoted to science and technology in quantum mechanics, which aim at just increase the awareness of all society towards the importance of quantum physics in our society. And I will try to say more about this. I would like to stress especially the point that science and technology enter here. So not only curiosity-driven research, but also their applications for, let's say, societal impact is something which matters in all the celebration that took place last year. The closing ceremony was last February. So why 2025? Because just 100, actually now 101 years ago, Heisenberg wrote his famous articles in which the formulations of what we now refer to as the formulation of quantum mechanics was given. This is actually the first page of this landmark in modern science, and those years were particularly important for the explosion of all ideas and research in the newly discovered, say, microscopic world. I mean, this is a picture of one of these famous Solvay conferences from 2027. And if you go through this list of people, I think several of them became Nobel Prize winners, and essentially they lay down all the foundation of what we know at present. I mean, there is Einstein, Marie Curie, Dirac. I mean, it's an impressive conference. 2025, as I said, was also the year in which these three gentlemen, John Clark, Michel Devoret, and John Martinez, got the Nobel Prize for Physics. Why? Well, they got the Nobel Prize for the discovery of macroscopic quantum mechanical tunneling and energy quantization in electric circuits, meaning that they were able to show that electric circuits under certain circumstances not only behave like what we are used to see in our daily life, but they can show quantum mechanical effect. This is the original paper that granted these people the Nobel Prize. It was published in 85, so 40 years ago. And in the next 15 or 20 minutes, I will trying to explain what does it mean macroscopic quantum tunneling and Josephson junctions. These are, I would say, the key words that are present in this paper. So let me say that at that time, in 85, this research was completely curiosity driven. There was no idea that this could be an important step towards quantum technological application. This came much later. At that time, actually, the equation was related more, as Giovanni said, more on the foundation of quantum mechanics. So on one side, I mean, if we go to the scale of angstrom or similar scale, we know that atoms obey quantum mechanics. So we take the theory developed by Heisenberg, Dirac, all these people, Schrödinger, and we can perfectly describe the properties of microscopic world. So on the other side, if we just, instead of considering an atom, we take a soccer ball, we don't need quantum mechanics. I mean, we just take the equations of that Newton found for us, and all the properties of the soccer ball are perfectly described. Well, somehow it looks like, and this has been a key question, and is still a key question to understand how to bridge between the quantum world and the classical world. I mean, there are several questions which are important. At the end, we know that a soccer ball is made of atoms. So somehow it would be very important to understand how things develop and progressively move from quantum to classical. Where is the barrier which separates, or where there is the crossover between quantum-dominated properties and classical-dominated properties? How this crossover emerges? What are the fundamental reasons why at some point the world that we know, where actually we don't need quantum mechanics, appears. Together with this, I think people also discussed how to push this boundary towards larger and larger system. Ideally, people started thinking how to find a bigger and bigger system that nevertheless, even if by looking at its dimensions would look like macroscopic, and then I will tell you a little bit what I mean, having objects that could still show quantum properties. Now, these questions and how to have objects, big objects, or bigger and bigger object that could show quantum properties has been explored in several ways. I mean, one characteristic which is really key to quantum mechanics is superposition principle. If you send a beam of atoms towards two slits on the screen, afterwards you will see interference pattern. While if you shoot a tennis ball, you will see an accumulation either here or here, depending on which is the slit from where the ball passes through. And so people thought, okay, instead of taking electrons or atoms, I will start taking bigger and bigger atoms, and people start seeing this interference pattern with big molecules like fullerenes. They also tried with viruses. So this was a way to try to move and see quantum mechanics in larger objects. The path that was seen by this gentleman that got the Nobel Prize was totally different. They started looking at circuits whose dimension, you see, is much bigger. I mean, this is 200 nanometers, so this is something like 1,000 on the scale of no, even larger, several thousands of in terms of typical atomic length. And these are what are called Josephson junctions. Inside, these are metals. And inside this, if you see it like this, it does not look really exciting. It's just a small circuit, okay? But what happens is really exciting. So in these small wires, there are many electrons, okay? And you can attach wires to these circuits, and you will measure current, voltage, in the same way as you do it in our electrical network. But these circuits are kind of special. These are made by two pieces of aluminum. Aluminum is a metal that at low temperatures, say below 1 Kelvin, minus 270 something, becomes superconducting. Superconducting meaning that the resistance, the electrical resistance, drops suddenly to zero. They can allow the flow of current without any dissipation. Now, Josephson, in his PhD thesis, showed theoretically that if you take two pieces of this aluminum in the superconducting phase and you just put a little bit of oxide in between, the system can conduct a current in a controlled way, in a way that it resembles the property of a giant atom. What I said is not correct, but let's say for the time being, I think it's fine not to be precise. Okay, so if you want, I can try to be more precise. So this is one example. So you have just two fingers of aluminum wires. There is some oxide. That's it. This is what becomes a giant atom. In the sense, if you see the dimensions, it's really 1,000 times larger. Already in the 80s, people, the first one who had this idea was Anderson, Nobel Prize for Physics, and then Leggett, thought that Josephson junctions were ideal system where to explore quantum mechanics in a macroscopic sense. If you, just to keep the discussion at symbol level, macroscopic means that you really see quantum mechanics by just doing measurements of current and voltages. The experiments that really proved that a Josephson junction or some connection of, so some variation of it really behaves like a giant atom was done much later, in early 2000s by a Japanese physicist called Yasunobu Nakamura. And this is a picture of the sample that he used to prove that really you just take a textbook of quantum mechanics, you just do a measurement of current voltages, and then you really see that this system is like a symbol atom. So let's see why this is so, and actually what Martinez, Clark, and Dvorec did to show the first step towards the realization of quantum mechanical behavior of Josephson, or just an electrical circuit. So for doing this, I just need to do just a small detour and say what is tunneling. Because the experiments of Clark, Dvorec, and Martinez was to show that you can measure the phenomenon of tunneling in a Josephson junction. Again, the theory which was very important in just anticipating was what was done later in the experiment, was done by Leggett, who just, by the way, passed away I think 1 or 2 weeks ago. So Leggett in the 80s really put forward the idea that quantum tunneling could be observed in a macroscopic circuit. Just let me very briefly say what is quantum tunneling. So just imagine that you have kind of potential, just a valley, and then you have to go over a ridge. Okay? Now, of course, you can climb and you just go to the top and go down. But you have other means that, for really macroscopic particles like us do not work, but if let's say they are microscopic but not that big, then it can happen that temperature can help in just going over the bridge. So even if the energy of this particle is somewhere here, now thermal fluctuations can just give a kick to the particle, and this kick is proportional to the temperature. So if you increase the temperature, then you have some probability that you are increasing your energy, and so you're able to go over the barrier. So the idea is that if you prepare a system, just a particle somewhere here, and then you want to know what is the probability to find it out here, outside the well, meaning that you went over the barrier, then the probability will heavily depend on the temperature where all the system is put. So it will go down, so it goes down exponentially with the temperature. A quantum particle does something completely different. A quantum particle is not described by a point-like particle, but actually is described by a wave function. So it's something like blurred around the position of the particle. So this is a phenomenon which was already understood really at the beginning of quantum mechanics. A quantum particle has the property to go through the barrier without going over the barrier. Meaning the probability, and this is related to the fact that the wave function, I mean, it behaves like a wave. So it's a kind of delocalized, and so it has some, it has a finite probability to be found here. Now, there are several important differences, but one thing which is crucial is that while the classical tunneling really depends on the height of the barrier compared to the energy that you can acquire by thermal fluctuations, quantum tunneling depends essentially on the width of the barrier and has no dependence on the temperature. Now, Leggett, together with his collaborator Caldera, did extensive calculation, I mean very precise calculations for a superconducting nanocircuit, and produced a well-detailed theory on how the probability to find the system outside the well would behave as a function of temperature. And this was what was measured by Martinez, Devore, and Clark. The experiment was done in such a way that essentially if tunneling occurs, then you just measure, you measure an electric signal. Now, this is the result of this paper of 85, and they measured, here you can see this is just probability to escape as a function of temperature. Now, here the straight line is what is predicted by thermal escape. So it's a straight line as a function, I mean, which relates the escape probability as a function of temperature. But you see that around few tenths of millikelvin, then the probability deviates So it's not anymore linear, it's not anymore, and then you see that you just look at these black dots, then it becomes flat. It becomes totally temperature independent. Of course, this was not enough. There was a detailed analysis showing that this big junction, this big piece of superconducting metal, a macroscopic system, would just behave like quantum mechanical would predict. As I said at the beginning, this was just curiosity driven. I mean, at that point, I think the main interest of Tony Leggett was just to understand the foundation of quantum mechanics, how classical behavior would emerge, or how much you could push the boundary of quantum mechanics towards macroscopic. Now we know that what in 85 was just pure science became a key element for today's quantum technologies. So let me just make this connection and try to tell you why this is so. So as I said, quantum mechanics plays a role in what we all these days call quantum computers and things like that. Now, let me specify that this is not new, in the sense that, I mean, quantum mechanics plays a fundamental role in technology since several decades. So for instance, in computers, if you go from the abacus to our daily, our laptops or computers, inside here, a computer, I mean, everything works because essentially we use quantum mechanical properties. Lasers have an impact in our daily life since their discoveries. But what is important is that here, at this level, for instance, in doing computation, quantum mechanics is only a mean to accelerate the computational capabilities. But if you want to do 1 + 1 or 2 + 2, the logical scheme, the algorithms to get the sum of two numbers is the same in the abacus and in a fast digital computer. It's just the speed. I mean, it is the speed which changes. Now, why then what Clark, Devore and Martinez did, why this was important for quantum technologies? What people refer when they talk about quantum technologies is something else. They refer to something which is also called second quantum revolution. They refer to the fact that quantum mechanics may not be only important in just building the hardware to make your devices faster. Quantum mechanics may be also relevant, actually fundamental, to really change the paradigm in which information is processed. At this level, if you want to encode any information that you want to store, manipulate, transmit, or whatever, the information is just a string or 0 and 1. Then the hardware, where quantum mechanics sets in, just manipulates classical zeros and classical ones. Now, just imagine that your circuits in which you encode 0 and 1 then shrinks more and more in such a way that it reaches the dimension where quantum mechanics becomes important. Now, either you decide that you have to suppress this quantum mechanical behavior, or you can say, okay, can I invent new rules that use quantum mechanics? This is what people did when they moved from bit to qubit. So going from bit to qubit means that you are changing the alphabet. So suppose 0 and 1 is you just use either up or down to label the information. Now suppose that instead of using up and down, you start taking all possible direction of your arm. Okay? So you're really changing the alphabet. You are changing the way you store information. Now, sometimes it may happen that, well, either use up or down, that's enough. Now, the question that people showed is that by using this infinite number of possible directions, instead of using North Pole and South Pole, then somehow the way you manipulate, store, and process information might be much more important. What people did by proving the existence of macroscopic quantum tunneling was to prove that a small circuit could behave like a giant atom, and therefore this idea of implementing this new alphabet associated to quantum information processing could be realized. Nobel Prize winner Bill Phillips just pointed out that when you think to quantum information processing, in his words, is a just radical departure in technology, more fundamentally different from current technologies than digital computers was from the abacus. It means that you can make a bike and you can say from, I don't know, 200 years ago, nowadays bikes are much, much faster, but essentially it's the same principle of operation. Now, instead of using a bike and make it faster and faster, you change it and now you start using cars. Okay? You have a different principle, and so it's not only improving the speed, but just really making possible things that were not possible before. What? What is it possible? I'll tell you in a second. First, a very brief and totally incomplete history of quantum technologies. Actually, I think the first people that started discussing, and they were just dreaming. I mean, in the 80s, like one of the initiators of this discussion was Feynman, and Feynman just by fun, I don't know, just said, okay, but why don't you use a quantum system to make a computer rather than a classical system to simulate a quantum system? In 84, these two gentlemen are Bennett and Brassard, devised the first way to do cryptography using quantum system, a secure cryptography. So one problem of cryptography is to share secretly messages. Now, quantum mechanics allows you to do this. as well as Arthur Eckert proposing a different protocols in 91. Now, a key step towards moving from just vague idea to concrete ideas, I would say, was David Deutsch. David Deutsch really thought well-defined ways to implement this quantum information processing. So he did the first step, he invented the problem where he could show that if you do calculations, or if you do, operations with these new rules, you do it faster than classical computers. But, well, nothing really still, it was still a very small community. People got really excited after 94 because Peter Shor, a mathematician in the States, showed that the quantum computer can factorize numbers in a more efficient way as compared to classical computers. Why do you care about this? You care about this because factorization, so the difficulty in factorizing numbers, so while it's very simple to multiply numbers, if you have a big numbers, you want to know what are the factors, this is a difficult problem, and this is the basis of why our ATM machine, ATM card is secure. So if once you know your PIN, then you can withdraw money, but if you don't know the PIN, and nobody just taking this card can steal money out of you. And actually banks got interested. Now, all this was just theory. The first two gentlemen that really start thinking on how to build up these devices were Sirac and Zoller, who made the first proposals of a computer using trapped ions. And then from there, it was really an amazing development of ideas and experimental realization of quantum information processing using different objects, using atoms, trapped atoms, ions, spin system, and using superconducting circuits. All the way, all this impressive progress was recognized not only through the Nobel Prize of last year, but several other key moments. So in 2012, there was the prize to Serge Haroche and David Wineland that invented ways to manipulate single photons and single atoms. And then later to, now I forgot the years, so late 2000, close to 2020 or something, I don't remember. But to Aspect, Zeilinger, and Clauser for experimentally proving what people know as Bell inequalities, essentially proving that all the weird things of quantum mechanics in a sense cannot be explained by inventing strange classical model. Again, all these were originally just curiosity driven. People never thought that they could become a key element for technologies. But nowadays, and here I just show two of the giants, giant company in the business, Google and IBM. They realize quantum computers with the race is growing. So I think At the moment, there are several hundreds of qubits just inside this cryostat that are operated, and with some discussion, so people are relatively well convinced that they already can do things that classical computers cannot do. Sorry. Now, quantum information is not only computing, so for sure, quantum computers can do much more than nowadays classical computers. And this is important because having access to more powerful machines means that you can start addressing problems which are at the moment difficult to understand, like material design, or just solve a complex problem in power management or traffic control, or study climates. I mean, at the end, all of this relies on the fact that you have powerful machines that are able to deal with these problems. But this is not only the case. I mean, quantum information also allows to make sensors more efficient and accurate sensors. I mean, there are experiments for detecting, let's say, small magnetic field variations. So this use kind of impurities in diamonds, and we senders in diamonds. There are gravimeters, quantum gravimeters, which are mountains, for instance, in Sicily, Mount Etna, based again on quantum mechanics, or very sensitive thermometers. So you may ask, why do you want to measure the temperature of a worm? This is, I don't know, but let's say this is something which is possible. You can transmit information in a secure way, or in a more, I mean, you can you can zip, say, information in a more efficient way. And nowadays, I mean, this is very old picture. I think it's the first example of quantum communication which was done under Geneva Lake. But nowadays, I mean, there are routinely experiments using satellites, and so this is, I mean, I would say probably quantum communication is the most powerful branch of quantum information technologies that is been realized. Back to superconducting qubits. Now I show you the first samples that granted the Nobel Prize to Dvorec, Martinez, and Clark. I mean, nowadays, as I said, in both in IBM and Google machines, the same principles, but with much different structure, has been developed in several groups. I mean, in Europe is in Delft, Saclay, but also in Chalmers, ETH, but also in the States, in Japan, China. I mean, this is already a very mature technology. The idea, I mean, originally people thought, okay, we should make this quantum technologies using atoms, but these are things which are a bit more difficult to scale up. A circuit has this natural virtue that if you just make a single structure, and this is not what is inside the computer, but if you make a single structure, you can make hundreds, thousands of it. And this probably is the key to scale up to a large number of qubits. So what is inside the IBM computer is more similar to this circuit. This would be the analog of a single qubit. It's just a wire, a resonator, in which inside here there is a small island superconducting. Everything is superconducting. All this wiggly line, and this is superconducting, and there is a small superconducting island with two Josephson junction, one here and one here. All this, despite its complication, really behaves like a simple two-level system, which is a textbook, probably the most simple quantum mechanical object that you may think. This is enlarged, the picture I showed you before. Of course, while the circuit itself is very simple, the connectivity and the connection of all these elements, the single elements that form the qubit, is very complicated. Not only, but what is very complicated is to keep all this at very low temperature. So inside here, so this is outside, but inside here, this cryostat keeps temperature of the order of few tenths of millikelvin. So in addition, there is a complex, very complex wiring that should take all the information which is somewhere here in the cold part of the sample, which is taking out and brings it there. And most important, all this should be very well protected from all sort of noise. Quantum system, even though they are macroscopic, still their quantumness is something which is it's a very fragile property which needs to be protected from all possible of noise sources which are all around the system. And with this, I thank you for your attention. Thank you very much.
Some questions? I have one. Can you just also, from the technical point of view, explain the transition from bits to qubits? So just tell us more about this change of, a protocol of structure.
So I just mentioned this. Let me say first something about alphabet. Okay, so you can communicate using Morse alphabet. So that is 0, 1, or just two signs, and you can construct everything. But for instance, if you develop a language, of course, a new language, so requires a new rules. Okay, so in principle, you can write everything which I'm saying now in terms of Morse alphabets, but probably it will take much. It's much more complicated, and then there are several things that you are missing in terms of meaning and the flavor of the discussion, so on and so forth. In a sense, going from bit to qubit is similar. So a qubit is nothing else than, instead of having a classical system that can be either here, or up or down, can be, being a quantum mechanical system, can be in any superposition of up and down. So any superposition means you can imagine just being pointing in just a generic direction, which is different from up and down. Now, this redundancy is a resource if you're able to use this additional infinite number of states to process information faster. And so this is indeed the case. I mean, this is not the only thing, but this is indeed the case by having a qubit. So for instance, something simpler, you can parallelize automatically the calculation, but quantum mechanics in addition also add to the fact that you can explore states which do not exist in the classical world, and this gives the real power of quantum computation or quantum manipulation.
Any other question?
So, I heard that there are some software simulating quantum systems.
Sorry?
There is a software simulating quantum
Yeah.
systems. Is this true or is this just some rumor?
No, this is true. Actually, no, this is true, but simulating a quantum system, it's very important to understand the properties of a quantum system, but still has not the same power as the quantum system itself. So your question, it perfectly fits with the picture of Feynman. Feynman was, so in 80s, he just realized, as many people understood, that if you take just a normal computer, this one or a supercomputer, does not matter, and you want to simulate a quantum system, it is very hard. It is very hard because you need a huge amount of resources to simulate the quantum system. So and the fact that you need a huge number of resources is somewhat related to the fact that the quantum system can be in any superposition of these states. So it's not like a classical up or down, but it's something more complicated. Feynman was the first one to say, okay, but since it's very complicated, why do you want to use a classical computer? Try to invent a quantum computer that has these huge resources built in, so it makes much less effort. And that's why he started talking about quantum simulators, quantum computer. Now, nevertheless, you can have simulators, classical simulators, as you mentioned, that simulate the quantum system. This is not the problem, but it's still something which can do only limited calculations.
I have a final question, if there is no one else asking. Do you think these companies, especially these startups, are overpromising with their application of quantum technology, since they're a lot of years and a lot of billions and there's no real application so far?
So this is a difficult question. Okay, so whatever I say, I will fail. But okay, I mean, this is recorded, so I cannot. So let me say the following. So first of all, there are directions in quantum information which are much more mature than others. So for instance, if you take sensing, the fact that you make very good sensors, this is something very well in the actual possibilities. Okay, and so I'm not able to tell you that it means that will be, I say, from a commercial point of view, advantage or not. This I don't know. But this is something that can be realized for sure. Then the application, I mean, if it's widespread or less or more widespread, it will depend on other factors, but this is not the problem. Quantum communication, so the fact that you want to share secret message, for instance, in cryptography, this is also something which is very well established. Now, if this is used as a small networks between banks, so it will become like a quantum World Wide Web, I don't know. Because I think that there are, so probably the technology will arrive there, but then you have to compare with costs. Your question is more difficult because you are talking about all the startups that are popping up, like I say in Italian, we say like mushrooms. I don't know if, okay. So most probably many of them will disappear. So which one, I don't know. But for sure, I think it's, so for instance, you take quantum computers. I think my impression that people are making more promise. I mean, not more promise in terms of final goal, but the fact that in order to be taking, well, I don't know if it's seriously, but if you want to create some attention, you say, I will make it in 5 years, and then instead of 5 years, it's 25 years. But so probably they are still, quantum computers are at the levels in which, so in order to really become powerful, you need to have a scheme for error correction to make quantum computers fault tolerant. They are the first experiment, so exists the scheme, but if you want to extend to make it large, still there is some steps to be done. No, but for sure, I agree with you that there is a hype. Okay, so quantum is probably too much, and in a sense, I think it will damage a bit the field.
Okay, I think that we can be close. So we thank the speaker. We mix